sklearn, cluster, meanshift. Description. Meanshift is a clustering algorithm that aims to find dense regions in a dataset by iteratively moving points towards the center of their neighborhood. It's a non-parametric method, meaning it doesn't require predefining the number of clusters like k-means. Inputs. X a 2D array representing the data points. Each row represents a data point, and each column represents a feature. Bandwidth. This parameter controls the size of the neighborhood around each data point. A larger bandwidth leads to more merging of clusters and fewer overall clusters. Outputs. Cluster centers. A 2D array containing the coordinates of the cluster centers. Labels. An array assigning each data point to its respective cluster. Steps. Initialization. The algorithm starts by defining a bandwidth, which defines the size of the neighborhood around each point. Shifting. For each data point, it calculates the mean shift vector, which points in the direction of the densest area in its neighborhood. The algorithm then updates the data point by moving it along this vector. Iteration. The shifting process is repeated until the data points converge to stable locations. These stable locations represent the cluster centers. Labeling. Once the cluster centers are identified, each data point is assigned to the cluster whose center is closest to it. Metrics. Silhouette score measures how similar a point is to its own cluster compared to other clusters. A score close to 1 indicates good clustering. Kalinski-Haraba's index measures the ratio of between cluster variance to within cluster variance. A higher score suggests better separation between clusters. Visualization plots. Scatter plot with cluster centers visualizes the data points with different colors representing different clusters. The cluster centers can be marked with special symbols. Dendrogram. While not directly produced by meanshift, a dendrogram can help visualize the hierarchical relationship of clusters found by meanshift. Fine-tune parameters. Bandwidth. The key parameter that determines the size of the neighborhoods and the resulting cluster granularity. Experimenting with different bandwidth values is crucial. Binseeding uses a binning technique to speed up the algorithm by initially clustering data points within certain regions. Uncertainty methods. Stability analysis by running meanshift with various random initializations or bandwidth variations. Observe the consistency of cluster assignments. Density-based thresholding. By setting a threshold on the density of clusters, you can identify areas of uncertainty where the density is low. Challenges and fixes. Challenge 1. Sensitive to bandwidth selection. Choosing an inappropriate bandwidth can lead to either overly fragmented clusters small bandwidth or merging of distinct clusters large bandwidth. Sample use case. When analyzing customer data with multiple segments e.g. age, income, a large bandwidth might lead to merging different customer groups into one. Fixes. Iterative bandwidth search. Experiment with various bandwidth values to observe the resulting cluster structure and find a value that captures the underlying patterns. Adaptive bandwidth. Implement a method where the bandwidth adjusts locally based on the density of the data. Challenge 2. Can be slow on large datasets. The shifting process can be computationally expensive, especially for datasets with many data points and high dimensionality. Sample use case. Clustering a dataset with millions of images can take a significant amount of time, even with a modern computer. Fixes. Sampling. Select a representative subset of the data to perform the clustering. This can speed up the algorithm while still providing meaningful insights. Approximate methods. Explore approximate meanshift implementations that trade off some accuracy for faster computation, like the mini-batch meanshift estimator. Parallel processing leverage parallel computing techniques to distribute the processing across multiple cores or machines.